season starts here, the Vancouver Boat Show.
All right, good afternoon. Thank you everybody for joining us. It's a pleasure to have you here at the VIBS. So I'm your moderator, Bobby. You can contact me anytime in the chat window for technical issues. In the meantime, you also have the Q&A box. You can type your questions in that Q&A box. And then when we get to the Q&A period at the end of the seminar, we will read out your questions. And now it's a pleasure to present Dominique Prinet with Marine Weather.
Thank you. Good afternoon. I'm Dominique Prinet. Thank you for being here. I hope you're not missing lunch. My first intention was to talk about politics and sex, and then I was told that it was too controversial and we should stick to more mundane topics. So we're going to talk about weather. I used to be a commercial pilot and a flight instructor in the 60s, and so I spent a lot of time teaching flying and navigating and weather to private and commercial pilots. And then in the last 15 years, from my retirement, I was a sailing instructor and instructor evaluator. And I taught sailing and navigation, coastal navigation, celestial navigation, and also weather. I just wanted to mention that you don't need to take notes or to try to scribble down web connections that I will show once in a while, because all the notes for the full course, the full weather course is 4 sessions of 3 hours. This is only 40 minutes. So the notes and the slides for the full show is available for you to download at no cost by looking at the chat box on Zoom, and you'll have a link. And if you click on that link, you will have access to the slides and to the links, which will, at the end of the presentation, allow you to download weather maps directly from your home on your computer as if you were on a sailboat. So it's good practice. Right, so this is the plan. We're going to talk about global circulation, fronts, winds affecting sailings, for instance, wind over current, or the Venturi effect. We're going to say a few words on storm and hurricanes, and then I will spend some time on weather charts and give you some ways to download the weather maps, the 2 types of weather maps available, so you can practice at home as if you were on a boat. So global circulation. This map is important because it shows the circulation around the world. The series of lows around the equator are caused by the heat of the sun. And of course, that series of lows moves north or south depending on the season. And the air goes up from the equator area and eventually cools off and then comes down around the tropics, around 30 degrees north, a bit north of. So the air comes down, which causes a series of high pressures around the Earth at about the level of the tropics or slightly further north. So good weather all the time because the highs are there year round, although they move north in the summer and they go south in the winter. And then the air, when it comes down and forms the high, goes back to the low to the south and moves north. And the air, moist, warm air, which comes from the highs, bumps into the cold, dry Arctic air, which flows away from the North Pole. So here you have a collision of air masses around the 60 degrees north of latitude, moving with the season up in the summer and south in the winter. So this collision of air masses forces the air to go back up again, and at the point of divergence, there is a lot of turbulence, which causes the jet stream. And we're going to see the effect of the jet stream caused by here. There is a slight jet stream here, but it's in warm areas and you can barely see it. This one is very strong, and that's what affects our weather at our latitude. So remember this pattern, because it is what governs the weather system around the Earth. So here's the cold, dry Arctic air. Here's the warm tropical air, and where they collide and the air masses are pushed up by collision from the collision of the Arctic air with the tropical air, it forms the jet stream, which turns around the Earth because of Coriolis. And this is what you see on television weather map, the jet stream at around 6 or 7 or 8 or 9,000 meters above ground level between the Arctic mass and the warm tropical air mass. So here's again the same kind of a map showing the lows around the equator, and then the series of highs along the tropic, and again the lows where the air is forced up because of the collision of the Arctic and warm, moist tropical air. The air is forced up, which creates a series of lows. And because of Coriolis, which is a force, it's not really a force, but it acts as a force, which moves everything to the right, the air coming out of the highs here turns to the right clockwise, and the air coming out south to fill up the lows down below turns right also. So you have down here what are called the trade winds from the highs to the low around the equator, and that's how you go from Europe to America. That's what Christopher Columbus did, just went down, picked up the trade winds and went west. Now, if you want to go back to Europe, then you have to go up through an area of highs where there is little wind, and then you pick up the westerlies, which are the winds coming out of the high and turning clockwise towards Europe. It is the reverse in the southern hemisphere. Now the fronts, if you look at the same map again here, you see that the cold, dry Arctic air and the warm tropical air collide. And that's a front line which goes around the Earth between the two air masses. So here's an expansion of it here. You have around 60 degrees north, depending on the season. You have the cold polar air mass turning clockwise here, the warm tropical air going down. That's just where they collide. They go up and form the jet stream. So this friction is similar to the friction between air and water. You've got two fluids which move relative to each other, but they have different properties, different densities. And therefore that creates a ripple. That's why we have waves on the surface, because of the two fluids flowing one against the rubbing one against the other. So the two air masses caused some turbulence. This is a vertical site that's seen from a satellite. The north is on top and the south is in the bottom. So at the front, you have a beginning of an oscillation. And as the oscillation increases, it's the same as on the ocean surface. Eventually, the amplitude augments. So here is the cold polar air north, here is the tropical air south, and the amplitude increases over time, and it starts with a little wiggle here and then gets deeper and deeper, and it forms a typical system as we see them, with the low and the front being twisted like this. And it's the same front which goes around the Earth. But eventually it breaks. And notice that the symbols for the front are different, because this is a warm front and this is a cold front. In fact, it's a continuation of the same front. But for the fellow who is here in the cold, dry Arctic air, as the front moves from west to east, the fellow ends up from the cold, dry air into the warm tropical air. So he or she says, ho ho, the air now is warmer, so I will call it a warm front. And when he or she goes from this warm tropical air back into the cold air, then he or she will say, well, the air is getting colder, I'll call it the cold front. So the warm front is always the first one, and the cold front is the second one, and they join at the center of the low, which is where the pressure is worse. Now we're going to take a look at the front globally. So I've drawn some of those oscillations over a map to show you the magnitude of it. Cold, dry Arctic air, warm tropical air, and here is your front, and the warm front, the cold front, and here there's a warm front again, because the guy from here to there sees the air warmer, and here from there it's a cold front. Now the particularities of the warm and cold front are totally different because of the way they are formed. So we'll make a vertical cut. So here's the system, 60 degrees latitude north, cold air, and here's your warm front and the cold air. I'll take a vertical cut across the front from a high altitude down to the ground surface, like a cut in a pizza, and we're going to see what those fronts look like. So here is the same area, cold Arctic air and warm tropical air. I make a cut like this, and this is what I get. Here's the ground, and this height here is about 10,000 meters. And here's the warm front, and here's the cold front. And the warm front tends to be very flat and very large, because the warm front here is made up of warm air bumping into the cold Arctic air. And the cold Arctic air is very dry and dense and is dragging on the surface, whereas the warmer air slides over it and pushes the warm front, but very slowly because it's heavy and drags on the surface. So the warm air flattens the edge of the warm front and make it a gentle slope as the warm air slides over it and eventually pushes it a little bit. Whereas on this side, you've got warm, moist air here, which is light and easily movable, and the cold, dry air, which is very heavy and dense and moves over the surface, and it's absolutely unstoppable, and it moves quite rapidly, often at the speed of a bicycle, for instance. It moves across the ground, and it pushes the warmer air and it pushes it straight up. So here is your warm front. Here's the cold air that you have originally, and the warm Arctic air sliding over it and spreading its moisture, and the slope is so low that it takes a couple of days for the front to go by, and the thickness of the front is about 1,000 or 2,000 kilometers. That's how thick the front is from beginning to end. So you start with little cirrus clouds and cirrostratus, and then you get thicker altostratus, and then stratus, and stratus get even thicker. And when it rains, it becomes warmer moisture. You get nimbostratus, it means rain. And here is the kind of cloud you see first, the cirrus clouds, and the cirrostratus with a halo around it, very thin at 10 or 12,000 meters of altitude. And then the altostratus gets thicker as the warm front approaches, gets thicker, the halo disappears, and then you get stratus and nimbostratus. You can see there is rain here. There's a nimbostratus. Whereas the vertical front is totally different because the cold air arriving pushes the warm air, and the cold air is heavy and dense and drags on the ground and moves in an unstoppable way and then pushes everything up. So the warm air is thrown up into clouds which are called vertical development. And here is a typical cold front cloud, the cumulonimbus. There's a lot of turbulence, there is hail, there's lightning, thunder, and when you fly, you don't want to fly through a cumulonimbus. It's absolutely awful. And here are the clouds that are associated with the cold front. Here is a cumulonimbus going up to 12,000 meters, and the towering cumulus, which are found. I flew around with a little airplane around Central and South America, and my colleague and I had to stop around 1 o'clock in the afternoon every day because of the buildup of moisture in the tropics and around the equator. It was getting so high and so thick and so turbulent. It was getting dangerous, and lightning and very heavy rain underneath it. So that's a towering cumulus which develops throughout the day. That's also very dangerous. It's called a finger cumulus. It's an indication that Mother Nature is mad as hell today. So you better get out of the way and return to the harbor. So here's the cut. Here is the warm tropical air which slides over the cold air, and that's a warm front. Here's your cold air, and here's the cold air from the Arctic coming back again and making clouds with vertical development. So the second thing I wanted to show you are the maps and the isobars. The isobars are the lines of same pressure. So you have Alaska here on the west coast, and Vancouver Island and this area and western US. So the pressure here is 1,036 hectopascal. Here it's 1,040, 1,032 going down, down, down every 4 hectopascal, 1,016, 1,012, 1,008, all the way down to the low here, which is around 980 or thereabouts, or even less than that. Notice that the isobars are very close, where the pressure changes very rapidly across the surface of the Earth. And tight isobars mean that the change of pressure is very strong, and therefore the air is pushed very strongly, as if you have a container with very high pressure and you open it up into something where the pressure is much lower, the air will rush out. Whereas if the change of pressure between, say, one room and the other is very light, then the air will flow very gently. So here the change of pressure across the surface of the earth is very gentle. Takes maybe 500 kilometers to move from 1036 to 1000. So no wind or very light winds here around the high pressure area. What's extraordinary is that it's in January. So this is why I took it there. It's quite extraordinary. So here is your low, and here is the occluded front, where the cold front pushes like a line of snow plow for is unstoppable and catches with the warm front. Here is your warm front, which is moving slowly, very long, 1,500 kilometers thick, and a very narrow cold front, which advances faster and catches up with a warm front, making an occluded front, which is a combination of cold and warm. So the Coriolis effect makes the winds turn clockwise. When they come out of the high, they turn clockwise because of the rotation of the Earth. And if it wasn't for Coriolis, we'd have no weather on Earth, because the highs would drain directly into the lows and fill up the lows, and that would be it. But because of Coriolis and the rotation of the Earth, the air from the high cannot go to the low. It turns right and it goes round and round, and it, because of ground friction, it tends to come out away from the high a little bit, but it's very hard for this high pressure area to fill up the low. So those two systems will stay side by side for days and weeks because of Coriolis. Here is a typical low west of Vancouver Island. It's always interesting to know where the low, if you're sitting on the west coast of Vancouver Island around here somewhere, it's always interesting to know whether the low is going to pass north of you or south of you. If it passes south of you, you're okay because you're away from the front. If the low is north of you, then you have to be prepared to cross the warm front and then the cold front. So the way to do it is to watch the wind as you're sailing, or as you hove to if you want. Watch the wind direction, and the way to do that is to look directly into the wind, and by feeling the wind on your ears, that's the way I do it anyhow, you can tell exactly where the wind comes from. So if you're here, for instance, and the system is moving from left to right, from west to east, the first wind you will see is in that direction. It's around the low, and it's pointing a little bit towards the inside of the low. And then as the system moves to the east, and you're still staying there, the second wind you will see is wind number 2, like this. And then you will see wind number 3. So over a period of maybe an hour or so, if you find exactly the direction of the wind, within an hour or two, you will see the difference of direction of the wind. Number 1, number 2, number 3. So you see the wind is backing, it's turning counterclockwise. You know you're okay. If you're doing it at the bottom here, if the low is going to go north of you, initially the wind will be this one, number 1, and then you'll get this one, number 2, and then you get this one, number 3. So number 1, number 2, and number 3, the wind turns clockwise. So you know you have a problem. You could have the low, warm front, long and tedious and getting thicker and thicker, and rain Nothing dramatic, but it's just going to be bad weather and rain and quite miserable. And then variable weather here, and then all hell will break loose when you see the cold front arriving with thunderstorms, and you better have your sails away when you cross the cold front, otherwise you'll come back with a broken mast or the sails will be torn off. It's quite violent underneath a cold front. So the way to do it is to, when things go wrong and you don't know what to do, you go on a starboard tack. Because it doesn't matter whether you're north or south of the low, if you take a starboard tack, you're going to be going away from the low, no matter where you are. So I don't have time to tell you the story, but one guy came back after a trip and he was so excited that at the monthly meeting of the association, he stood up and told his story. And he said, look, it was getting so bad, he didn't know what to do, but he had taken the course on weather. And the one thing he'd remember is that when things go wrong, take a starboard tack. And he said, after about 12 hours, it was getting better. And after 24 hours, I was beginning to see the light at the end of the tunnel. And I was, after 48 hours, I was out in the good weather. And he was like preaching. He climbed up on the stage and he was like some of the churches you see down in the States. He had seen the light and he had been saved and he wanted to tell everybody. So I was in the room, so I was a little bit embarrassed and everybody laughed, but that's all he remembered from the course. When things go wrong, you go on a starboard tack and wait 24 hours and you will be saved. Now the isobars, when they're very close, they generate a strong wind. When they're very far apart, the winds are much lighter and there are scales to help you with that. So here's a typical weather map. The one before I had cleaned up. This is a weather map. So here's Alaska, the Aleutian. Here's western side of Alaska. Here's BC, Vancouver Island, and down there. So this is typical again. You have a low, and that's in December 2005. See, I was already telling lies at the time. Here is the low, tight isobars. Notice it says storm here, which means the isobar is very tight. This little triangle means 50 knots of wind from the west-northwest, turning counterclockwise, pointing a little bit under the low, into the low. And here is your occluded front and the warm front here, and the cold front behind. So the winds affecting sailing, wing over tide. I've been caught several times when there's a change of tide and nice summer weather going up and down the coast. Everything is honky-dory because there's a slight breeze in one direction and the tide is in the same direction and there's nothing to it and everybody is smiling. And then the tide turns, same wind, 5 or 10 knots, beautiful day, no problem at all, nice weather, little birds are singing, everybody's happy, and all of a sudden the tide turns and the waves become absolutely miserable, very short and very steep. So when you want to go from here to the other side, to Vancouver Island, watch the wind direction, but it's not so much the strength of the wind, is the wind with the tide or against the tide. Coastal winds, that happens a lot in the tropics or in Africa. I did quite a bit of sailing from East Africa. I was there for 5 years and I had my own little sailboat. And it's the same pattern every day. The heat causes the moisture to go up and condense. You get clouds over land. This is how, from a distance far away, if you see a line of clouds on the horizon, that's probably land. and so that creates a vacuum and it causes a sea breeze. So if you have a little island there and you arrive at the end of the day, there is a sea breeze, so you park on the lee side, downwind where it's sheltered, and then you go to bed. And then at 2 o'clock in the morning, the pattern reverses, and you see people jumping out on the deck in their baby dolls and pajamas, and try to get the anchor up and then move to the other side because it's unbearable. They're being bumped on the rocks and it's becoming dangerous. So they've got to move to the other side of the island. I'm talking from experience. Another phenomenon is that you get compressed air along a chain of mountain. So you've got to stay maybe at least maybe 10 nautical miles, maybe 20 nautical miles away from shore if you want to have lower winds. Katabatic winds are caused in the spring when you have snow and ice on top of the mountains and it cools off at night. So the cold air slides down and accumulates and then flows out. And you get terrific winds in Howe Sound at 2 o'clock in the morning in the spring when there is snow and ice on top of the mountain. It's been nice and warm during the day and then it cools off at night. All the air flows down and you get winds of 20, 30 knots, even 35 knots. Out of nowhere, there's no wind anywhere else. I mean, it's a beautiful day, etc. It's just local katabatic winds. And I've been caught with students in there, and all of a sudden, there's no wind anywhere in the region, except that it blows at 30 knots down Howe Sound. So be careful when you overnight. Another phenomenon which you have to remember is the Venturi effect. When the air goes through a constricted space, then it creates a suction. You see the water level goes down here. It's used for vaporizers when you blow air through a narrow gap of the pipe, then it creates a vacuum and then the perfume or the alcohol is sucked out. It's the same as a carburetor. A carburetor works this way. So if you're flying, for instance, in the Caribbean, and I got caught exactly like this, flying in the shadow of in the lee of the islands where it's nice and peaceful under spinnaker with students, and all of a sudden I forgot that there was a gap and the Venturi effect made the wind blow like hell. Between the two, it was just being accelerated by the gap and you got knocked down when we got through. It was my error. I should have thought of it. And if there's a channel, then the wind will accelerate in the channel. Storms and hurricanes, it's the same. It's not along the equator. There is no hurricane or cyclone along the equator. It's north or south of the equator. There is nothing along the equator because there is no Coriolis force in the equator. It's maximum at the pole and it's zero around the equator. So if you don't know which way to go away from the equator, if you don't know where to go towards the equator to get out of the hurricanes. The most dangerous quarter is this one, the northwest corner. If you have a hurricane going, say, towards Cuba, for instance, typically, that's because the wind turns counterclockwise and the wind speed around the low here is added to the displacement, to the speed of the hurricane itself. So you got maximum speed and compression up here. And you check which side you are by watching again how the wind changes. And with the hurricane, all you have to do is wait maybe an hour or two. And if the wind changes from 1 to 2 to 3 clockwise, then you're northeast. and you've got to get out because that's the dangerous side. If it turns from 1 to 2 to 3 counterclockwise, then you're okay. The weather charts. There are two types: the Raster charts and the grib charts, produced by computer. And this is produced initially by computer, but it's polished by hand. So the source of weather charts. Here is the link, which is at the last 10 pages or 8 pages of the notes have all these links. So from the comfort of your home, if you click on this link, which is in the notes, you will have access instantly to these charts. And those are raster charts. They're lines drawn by hand or drawn by machine. A few years ago, they were in black and white. Now they come in color. So this is Alaska. This is the West Coast. This is Vancouver Island. And Hawaii must be around here somewhere. This is the whole Pacific. And if you click on this half of the picture on your screen at home, you get this half of the Pacific. That's the one you're interested in. Here is Alaska and the West Coast and Vancouver Island. So here's your low, and it says hurricane force. You can see how tight the isobars are here. And here is your, so that this system has been around for a while. So you see the wave is dying. It's all curled up, and this is the occlusion, and continued with a warm front and the cold front behind. Notice the isobars are in a straight line here between the two fronts, and they curled around the low. So what you do is to download them, you click this link again in the notes, you click on it, and then you type help on your email. You use your email. This is the address for the email. You type help, and you get the list of all the weather maps available by time, by area, by type. And once you choose one, for instance, the 18 Zulu surface analysis Northeast Pacific, here is the number. So you send another email, says open change directory to the fax area at NOAA, and you say get, and then you copy this name, PYB, etc., and then quit. And within seconds, you get, and it's free, you get the FTP mail, and here is the file, and it's a tiff file. So you click on it, and this is what you get. So you should try it because it's very exciting. You do it instantly. All you have to do is click on a couple of links. You choose your weather map, and this is what you get. So I did that just a few days ago, well, a month ago, when I was preparing this session. And the grid chart are computer generated. So again, you will see in the notes, you need 2 little programs that you need to download, and you click on one, you get this, you draw the map that you're interested in, the area you're interested in. This is where my boat is. I just tell you where is your boat, and then you want this area, or you want this area, or you want South America. It doesn't matter, any area you want, and the type of grib file that you want, and you send it off. And they ask you, this is the definition of the area that you're interested in. They ask you how precise you want the map to be. Every 3 degrees of latitude, little squares of 3 degrees latitude by 3 degree longitude, you can go down to 1. So it's 1. So that's every 60 nautical miles, you have a little arrow showing you the wind. And you want the waves, you want the wind, and you want the pressure at mean sea level, and you send it off, and this is what you get. And I did that at the same time on the 13th of January. This is the grib file. And this is what you get. And again, it's free. And you do that at home, and it's all very exciting. You can find the weather in Australia, etc. And but it's produced by computer. So the computer is not very smart and doesn't tell the difference between land and ocean. So it's the same type of arrows across Vancouver Island and across the Rocky Mountains, because the computer doesn't know the difference between the mountains and the ocean. But if you're on the water, then it becomes quite accurate, and it's very handy. 1 minute of advertising. If you're interested in coastal navigation, there's a fabulous book here. And coastal navigation exercises. And the same thing in celestial navigation. Here is the course, and here is the exercises. And I wrote here, as will be seen in the French exit. By the way, it just came out a few days ago, the film with Michelle Pfeiffer. They called me from New York last year asking me if they could use my book of celestial navigation for their film, The French Exit. And I was baffled, because like asking if you can use a telephone directory to make a movie doesn't make any sense. It's totally unreadable, full of numbers and digits and graphics and tables. We said, we're only interested in the cover. So I said, sure, go ahead. And so there is a scene apparently at the wheelhouse where the captain and Michelle Pfeiffer are discussing things. I don't know what it's in the around 1920s across the North Atlantic on a big ship like the Queen Mary, apparently. So presumably my book is on the table somewhere. So when you see the movie, you just jump up and down in the theater and say, hey, I know the guy who wrote the book there. So it's available from all these good places. And the last book, Fabulous Stories, Bush Flying in the Arctic, that just came out a few days ago. Right, and that's the end of my story. Thank you very much. And I'm open to questions.
Thank you so much, Dominic. It's been very gripping, I think, and fascinating to watch this. So in the meantime, we did have some questions in the Q&A box posted. We have Catherine Pedersen asking, why does warm front B on slide say cooler air? I think that was approximately the 27th, 28th slide. I couldn't be sure though. It's blue and red, I remember.
Yes. Yes. I know, yeah, cool air.
There it was. I think the one after that, or this one maybe.
Yeah. Cool air. This is the cold air from the Arctic, and then the warm tropical air comes over it. And you see, this is the cold Arctic air in the whole area up there, cold air. This is the one under the front. And then the warm air pushes it and slides over. And here's your warm air. So colder air, warm air, and then back to colder air when you cross here. I think that's the only, yeah. Here is your cooler air in the Arctic and the warmer air, tropical air.
Okay, so Catherine has a follow-up question. She says, and why is cold air heavy and dense?
Cold air is heavy because it's dense. The density is higher when it's cold. So it sinks, cold air goes down. This is what happens with the katabatic winds. So cold air from the top of the mountains and snow gets heavier, dense, and then falls down, it sinks. And the warm air is air which is expanded, like the air in a hot air balloon, it expands. So its density decreases, and it becomes relatively lighter. So you have a hot air bubble which floats up. This is what gliders use when gliders are flying across the countryside and they start losing altitude, they look for a wheat field, which is nice and warm because of the heat of the sun in the summer. And over a wheat field, you get hot air going up, and you'll see the eagles and the gliders turn up over the wheat field in altitude because the air is warm and dilated and lighter and goes up. When the air is cold, it gets denser and sinks.
All right, great. So we have several more questions. We have Mike Evans asking, can you describe the wind directions 1, 2, 3 in slide 27?
Yes. Yes, in slide 20. Here is this. You say you're here. Your boat is here, and it's fixed at anchor. And here is the low, and the low typically moves from left to right because of Coriolis and rotation of the Earth. So all the systems come from the west and go. So if your boat is here, as the air is turning counterclockwise around the low, you see the wind is not tangent to the isobars, but because of friction is pointing a little bit towards the inside of the low. So here is pointing a little bit inside, and here is top part. So this is the wind going around counterclockwise around the low and pointing a little bit inside. So as the movement, as the whole system moves west, the first wind, if you're stable there, the first wind you will see is wind number 1, which is in this direction. And then as the system moves east, from the west, you're going to see this wind. This wind will move to you, and you will see wind number 2. And then eventually, this wind, after say 24 hours, will arrive to you, and it'll point in this direction. So the wind starts flowing this way, and then that way, and then that way. Starts turning counterclockwise. Whereas here, the winds are exactly in the opposite direction. They turn clockwise. So you can tell whether you're on the north or south side of the low by watching the wind veering or backing. And it's the same thing if you're being hit by a hurricane. Depending on whether the wind is veering or backing, you can tell on which side of the hurricane you are. Does that answer your question?
So that was Mike Evans. Mike, you can follow up in chat, or if you raise your hand, I can open your audio. Otherwise, okay, here's Mike. Please unmute. Go ahead.
Hello. I just wonder, what is the wind direction at point 1 and point 2 and point 3? Is it at point 1, is the wind northwest?
No, it comes from the southeast. It points to the northwest, and it's got the barbs. It's like an arrow with the barbs feather in the back and the pointed. So the wind is, I should have specified, goes this way towards from the southeast to the northwest. The winds turn counterclockwise. So in this area, it goes this way. This area, it goes that way. And here, it goes that way.
Okay, I understand. Thank you.
Okay.
All right, and now we have David Hopkins asking whether you have any suggestions for getting more local grib files. And he says, is this necessary if you're staying local?
Yeah, if you're local, you just do what I do. Look, get the notes and the link, and then you get the grib files for whatever area you want. Remember that it's computer designed, no human intervention. So when you get into mountains and valleys, what you get is absolute garbage. But as long as the surface is flat, like in the prairies or on land, away from shore on water, then it's quite accurate.
Okay, we have Christian Young. Can you recommend a good grip viewer?
Yes, there's ViewFax, which comes automatically with Sail Mail. So they're both free, they're excellent, and you need the two programs, one to download the grip files, the other one to view it. And the programs and how to get them, they're free, is listed in the notes.
Okay, and we have Keith Jeffrey. I'm always surprised by calm evenings and nights in anchorages despite fronts. What the relative influence of diurnal winds versus fronts?
Well, they're not related. Diurnal winds are caused by the heat of the sun during the day, and during the day the earth heats quite rapidly, whereas the ocean or the sea remains at a constant temperature. So at the end of the day, or say at 3 o'clock in the afternoon, you get maximum heat over land, and you get updraft, which increase during the day until the middle of the afternoon, and then they die down in the evening as the Earth's temperature stabilizes. And that's a cycle which is reversed at night when the Earth cools off and the ocean or the sea remains fairly warm. So that's a cycle which occurs especially in the tropics and in the equator, when the heat effect of the sun during the day is quite high. The fronts, the winds caused by the fronts occur only when a front happens to move by, and that could happen maybe every few days, or it can not happen for weeks. So that depends on the structure of the upper atmosphere and the jet stream. That the jet stream is what affects the weather down below. I don't have time to go over it, but the oscillation of the jet stream cause the wind in altitude to accelerate or decelerate, which causes a suction or a compression, which causes the lows down below or the highs down below. So we're all dependent on what happens at 8 or 10,000 meters above sea level.
Okay, and we have Mike Evans asking, what is the direction at 1 northwest? I think he's probably referring to the same slide he talked about earlier.
Is it?
Oh, here's Mike's hand up, but one moment. He can clarify it, actually.
Yes.
Thanks, Dominic. You already answered that one.
Okay.
Okay, and Mike, what about the next one? At 2 wind is west?
Yep, all three. I'm good with those three. Thank you.
Okay, perfect. Thanks. All right, we have Spike asking, what is the prevailing wind direction in the Arctic at the Antarctic and the Antarctic?
In the Antarctic, I've never been there, but I've spent years in the Arctic, so I know. That's why you should read my book, by the way. It's all the stories about the Arctic and high Arctic. The winds along the Arctic coast tend to come from the west. That has been my experience over the years. But the interesting part is that in the high Arctic, there is relatively little wind. And in fact, it tends to be calm most of the time because the air is very dense and very heavy, and then it sits there. and so it's there are no fronts up there, and it's just cold, dry air. It's like a desert. It doesn't rain, it doesn't snow. It gets very, very cold, and there's very little wind. But whatever wind there is tends to come from the west in the Arctic. So I suspect it's the reverse. In the Antarctic, it probably comes from the east, but I don't know.
Okay, and here's Stephen asking, when the Georgia Strait has strong winds, it is usually in the morning. Is this because of the cold surface air meeting the warmer air?
When there's an evolution of the wind velocity and direction during the day, if there is no front coming by, then that's a diurnal effect. That's exactly right. That's the sun gradually heating the land mass and creating hot air, which dilates and rises, creating a vacuum. So it increases the airflow from the water. And the Georgia Strait, the wind is guided by Vancouver Island and by the mountains along the shoreline on the mainland. And so they are guided by those two ranges of mountains. But unless there is a front, then that's diurnal. It's the effect of the sun.
Okay, and let's squeeze in the last question here from Al Horvath. And he's saying, we sail on the Diefenbaker Lake Reservoir in Saskatchewan. Is there similar downloadable weather maps or land-bound waters, and are they reliable?
Yes, in the prairies, you will have the maps. You have the same raster black and white maps from NAAA, and you'll have the same, and they're reliable because they're being adjusted manually, each of them. And the name of the fellow who makes the adjustment is written on the map. And the grib files, because it's flat terrain, are also relatively reliable because there are no obstacles which falsify the results. So as long as it's flat terrain, then the grib files are okay. And so you get the same set of miles of maps for whatever place you want in anywhere.
All right, well, this brings us to the end. Dominic Prenate, thank you so much for a great presentation, and everybody who attended, thank you for joining us. It's great to have you here, and please be sure to check out all the features at VIBS. If you have a question, check out the info booth also, and online you'll find a lot of information. I hope you have a great day at the boat show.
Thank you. Thank you all.